Welcome to this session on designing events first microservices. My name is Jonas Bonér. I'm from Uppsala, Sweden. I'm the co-founder and also CTO of Lightbend. We create, the ACA project, a project that I started almost 10 years ago now, actually. And the Play frameworks, we developed Scala programming language and things like that. But I'm here to talk to you about microservices. I assume that you're at least somehow interested in microservice, in how to do it better or to learn about it from the get-go, so to speak. First I want to say that I hope that you're interested in microservices for the right reasons. I mean, microservices it's a very powerful sort of approach to building software that has a lot of implications, but it's mainly, I think it should mainly be used as a way to scale the organization, to chunk up your organization into autonomous teams that each can sort of develop software independently of each other and roll out and sort of redeploy and upgrade and sort of maintain its services independently of each other. To higher velocity as an organization, rolling out features, with this loosely coupled architecture and loosely coupled teams, so to speak. So teams don't block each other, time to market and all of these things. But unfortunately, when it also has big implications on your architecture, or fortunately, you can say, if you apply the right sort of design patterns. I think it's important, that that you don't make sure that you don't end up with what I call microliths here, where essentially you'll split up your monolith, but just sort of maintain the strong coupling between your services. So you end up with sort of a hybrid in which you inherit all the hard things with microservices, but still sort of bring along all the bad things with the monolith. Things like fully synchronous and blocking calls between microservices, things like fully synchronous and blocking calls down to the database, often even having one single database, actually, I've seen. And the problem with this is that it couples to your system quite a lot, and it limits things like scale, availability, extensibility, and maintainability, and all those things that you can actually that you have an opportunity to actually solve with the microservices architecture. I think we can generally do better than this, and I think events can actually help us along the way. And this talk is really about how to think in events and how to sort of design your system around events and how events sort of can liberate a really good design, sort of pave the way for a really good design for distributed systems and microservices in general. So I try to look at sort of events from a domain-driven design perspective. How many here have heard or have sort of applied, or rather say probably everyone has heard, applied domain-driven design to some extent? Okay, so about I think most people. I mean, domain-driven design, DDD. It's a great tool. It has really served us well the last what is it 15 years or something like that. But it can easily sort of lead us down the wrong path, I think, because it puts focus on structure, on the things too early in the process. I'll get more into detail what I mean about that. So I think that focusing on events is actually a way to sort of make domain-driven design really useful and valid and applicable to today's more modern systems that are distributed, that needs to be where you have these autonomous components and things like that. Okay, Greg Young, is one of the spokespersons from DDD, in DDD for quite some time. He said that when you start modeling events, it forces you to think about the behavior of the system, as opposed to thinking about the structure of the system. So what I think is we should apply this and not focus on the things. We've been taught to to focus on the things, you know, from object-oriented design. I mean, I was taught that that you should really try to find all the nuns, etc. You know, because they are your objects, your domain objects in DDD. But instead, you know, we should try to focus on what happens in the system. You know, find the verbs, and these verbs are often represented then as our events, because you know, it's in what happens that's really where the most action is. That's really the things that are interesting. Those are the things that represent business logic and how information flows in the system. You know, data is king today. Data is more valuable than ever, and how it flows and how to manage that properly, not only at rest but actually in motion, is really one of the key aspects of modern software design. But what is an event then, if we should start with the basics? Yeah. An event is sort of an immutable fact of information. You know, knowledge can only grow. I can only learn more. Sure, if I, you know, I can perhaps sometimes forget, but in principle, I can only learn more, you know. So facts accrue. They accrue over time. Okay? And events, facts. So I talk about them sort of as being the same thing here, because events represents facts. Okay, but facts, they can be, of course, be disregarded and they can be ignored. You might have a sort of a reason to believe that whoever you're talking with is lying, for example, or you might get conflicting information and having to throw one sort of fact away and sort of take the other one in, so to speak. Events, but I think it's really important, you know, that once events has been sort of accepted as being the truth, they can't be retracted. Okay? And also events can't be deleted. You can't erase knowledge. Okay? So once you have accepted it, it can't be deleted. Of course, you know, with GDPR and everything, there might be reasons that for us software engineers to delete facts for moral reasons, for legal reasons, and things like that. But the conceptual framework of how I think about events is that they can't be retracted, they can't be deleted. However, naturally, new facts that arrive into the system can, of course, invalidate existing facts. That's how knowledge evolves. Okay? Are you with me? Great. So we should sort of try to learn to mine the facts in the design process, just like a detective coming into crime scene and say, what are the facts? I mean, what led to what, etc. All right, and one sort of technique that's been popular the last 5-6 years or so is a technique called event storming. That's really, it's quite simple. You bring in all the stakeholders, all the programmers, you know, all the domain experts in one single room. You give them a bunch of post-it notes and let them sort of brainstorm essentially about trying to what happens in the system, trying to find the events, try to find the domain language through the events. Okay, understand how data flows, who's talking to who, how communication patterns arise, and things like that. And very important to understand causality. You know, X happened, that triggered something that sort of some sort of an effect in B or in Y, etc. Right? And we are in the process of doing so. We're really trying to understand mainly two things, probably more, but at least two things. First, the intents, you know, and when we sort of try to mine and understand the intents, good things to look for here is things like communication, conversations, expectations, contracts between sort of two parties, transfer of control. I'm handing over control to someone else, you know. And the other thing to look for is facts. You know, facts are things like state, history, causality, notifications of some sort, and transfer of state from one party to the other. You know, and the intents are very often represented as commands, while facts are represented as events. So this is sort of a path towards trying to mine and understand where do I have my commands, and in which context do they apply, where do I have my events, what caused them, etc. Okay? But let's try to understand commands and events a little bit better, dig a little bit deeper. Commands, is sort of the object form of a method or some sort of action request. Okay? There are a verb, but they're usually phrased in the imperative. Things like create order or ship product, sort of an imposition. You're telling someone to do something. Okay? That's a command. Command usually triggers some sort of side effects, some sort of reaction. Okay? And this reaction then, out of that reaction, we create an event representing the fact that we did something, you know? Because events always represent something that has already happened. And therefore, they're sort of phrased in past tense. Things like order created. I have already created the order. That is a fact. Product shipped. I've already shipped the product. And things like that. Okay? So command versus events. Commands are really all about intent. I intend to do something. I oblige you to do something. I ask you to do something. Events are completely intentless. Commands are directed. Events are completely anonymous. Why? Because commands, they're sent to a single addressable destination, while events just happen, for anyone to observe. Can be 0, can be 1, can be 1,000. The one that emits the event doesn't care. It just emits the event. Here is a fact. Anyone that is interested, listen in. While commands are really targeted information. This means that commands model personal communication, one-to-one. But events, they're more like models broadcast, just like sort of me here, sort of just throwing out facts, and it's up to you to take them in, or surf on your phone, or zoom out. Commands, they sort of have a distributed focus, while events have a solely a local focus. This is really important as well. And I think the reason why that is that, commands, they cross address spaces, and they model, so commands are addressable. You send them to a direct destination. So they are really useful in distributed setting to communicate across context, right? While events really have a local focus only emitting locally. They need some sort of other layer to relay that event across address spaces if needed, so adds more infrastructure. So commands are really only about command and control, while events are all about autonomy. And a lot of people talk about autonomy when it comes to microservices, and autonomy is the really hallmark of good design in distributed systems. You want autonomous components that can be in charge of their own destiny, so to speak. They can be upgraded in isolation without sort of breaking up this strong coupling that you sometimes have between components. So I think events can really put us on the path towards more autonomy. When it comes to a DDD context, then these components, they're often defined by sort of some sort of bounded context. And I won't go into to what that means, but it's sort of the boundary for our domain language, for our little domain model for this specific service. And I think we should really let our events define these boundaries by defining well-defined protocols for which events I can accept and which commands I accept, or which events I listen to, or which commands I send out, or which events I emit, so to speak. And if you focus a lot on events, the interesting thing is that sort of inverts the control flow from obligations, where I always tell someone to do something and I'm on the receiving side, always react to someone. It sort of inverts the control flow. So I'm in charge of my own destiny. I can listen into events, and I can choose to accept them, I can choose to do something, but it's my choice. And this inversion of control is really what gives autonomy. Okay? So what are the characteristics of an event-driven service? Yeah, they receive and react to facts that sort of come his way, and as I said before, when I talk about facts, I really talk about these immutable events. Then they are the same thing. I publish new facts to the world asynchronously whenever I find something is worth for others to potentially react to. as I said before, this inverse the control flow, right? So one key aspect here, and one question that I always get, what about, you talk a lot about immutable events, then what about mutable state? Because we as software engineers are very often taught to think in terms of mutable state. And you know, there's a lot of people talk about functional programming, and you know, some people there always say that, you know, really shy away. It tells you to shy away from mutable state. You know, that you all go immutable and things like that. I think that, you know, mutable states can be problematic, but I think it can also be totally fine as long as you contain it. Okay. And I also think that events can help here as well, because if we we receive events, and if we then contain our sort of mutable state into local computations, then we can sort of publish facts then to the outside world, representing what the result of whatever computation we came up with as immutable facts. So that you have this boundary that within your sort of box, your service or whatever, you can just use mutable state. But whenever you communicate with the outside world, you do that through stable values, through facts. So others can sort of reason about what you came up with, or the processing, the result of your processing, you know, based on stable values that don't change. Okay. And in DDD terms, so the way to model this is to the aggregate. The aggregate can really become, or it can really be our sort of boundary where we maintain integrity and consistency of our data model. It is our unit of consistency, our unit of failure, our unit of determinism, and it can be fully autonomous. I'll dive in a little bit more into this later. Okay, so event-driven services. So one way is to try to explain a little bit how they work in context here. That let's say that you have some sort of user. That can be another service, that can be a human, or whatever, it really doesn't matter. But somehow a command is sent to this service here then. That ends up on his mailbox or in his queue or something like that, you know. And then, you know, it's picked up and some processing is done. It probably updates its internal state to some extent, you know. And then an event is created out of that represent what actually happened just now, the effect from reacting to the command. And that is now sent to the event stream. And the event stream, you know, can relay that to whoever might be listening in, whoever might be interested. There can be other services, as here, you know, that reacts to this event. It can be that you know, that we shove the events down into a database. For like, for example, Hadoop, for batch processing overnight, you know, for doing mine the data that we have sort of emitted, or it can be external services, so you can use it for integration type of purposes, etc., etc. Like, use your imagination. It can really be used to do so many different things. But it's really important here, and I'll get back to this, is that all this, you know, as soon as you start emitting events, that happens in an asynchronous fashion. So that means that we have eventual consistency here. You know, it will take some time for that event to propagate. And you should not use transactions unless you absolutely have to here. Okay. But so this event stream can be extremely useful. It can be really foundational building block in an event-driven architecture. Because you can use it as a communication fabric. You can use it as the integration fabric, communicating with outside systems or whatever. You can use it as a replication fabric to replicate the events, you know, into hot replicas of your services. That the load balancer can then, you know, redirect over to whenever a failure occurs. Okay, you can use it as the consensus fabric, a way to make sense of state in the distributed system, which is one of the harder things that we need to deal with. You can also use it as the persistence fabric. I'll get down to some of this. I won't cover all of these things, but I'll definitely cover some of these later in this talk. So it's a really good building block. You know, but some people then think, okay, events for persistence, right? But why can't I just use CRUD? I'm used to use CRUD, and CRUD can absolutely be fine in an event-driven context. And I'll get back to how just in a second. But first, I want to outline some of the problems with CRUD services in a distributed systems, right? I think CRUD, you know, create, read, update, delete, meaning storing state straight down into a regular SQL database. Okay, it's fine for totally isolated data. The problem is that very seldom state is completely isolated. It can be, and then CRUD is totally fine for your services. But it can be problematic when you need for cross CRUD consistency. You know, when you need to have consistency across different services. When some other service reads your data and does something with it, etc. Right? Because it's really hard to do joins. It's really hard to actually guarantee much of anything, I believe. And this is one of the problems that I think events can solve. You know, reality continues to ruin my life. You know, and one of the reasons why it's hard is that, you know, as Pat Helen said, that two-phase commit is the anti-availability protocol, because as soon as you start introducing transaction across services to maintain, you know, the atomicity of CRUD across a distributed system, availability suffers. You know, because I mean, it introduces this sort of temporal coupling and things like that, and it easily starts to fall apart. And I think strong consistency absolutely has its place within the aggregate. But it's the wrong default in a distributed system. Even though it's often what we as programmers just by habit reach for. You know, we're used to thinking in terms of strong consistency, since have been spoiled by the monolith for so long. But you know, when we move to microservices, all bets are off. We can't assume the same things anymore as we did with when we had, you know, monoliths sitting on top of one single database. Then it was easy. Now, in a distributed system, I think that, you know, you need to completely rethink, you know, consistency, your consistency guarantees, and try to loosen them up. And very often when we do so, I must say, we realize that we actually didn't need strong consistency everywhere we thought we did. You know, it's actually not how the world works. We just try to shoehorn the world, you know, into strong consistency just out of habit. So what can we do then? Yeah, I really believe that we have to rely on eventual consistency as the default and opt in on strong consistency when we can. You know, invert the relationship instead of doing the opposite like many people do. Okay? Oops. Because I really think eventual consistency is really how the world works. If we try to model something in the real world to software, it's very often the most natural way to model it is through eventual consistency. And I think in general, I mean, since distributed systems very much match how the real world works, you know, the real world is inherently distributed. We have to embrace reality when we try to model and design distributed systems. It's really how the world works in general. So, one example, for example, is that information in the real world, you know, has latency. And of course, I mean, we as programmers, we are affected by that every day. That information travels at the speed of light at best, you know, very often considerably slower. And this is a hard limitation that we as software engineers need to take into account. You know, latency, especially across data centers and stuff, is really measurable and has a strong impact. And what this means, you know, is that information, whenever we receive it, is always from the past. It has already happened, often quite some time ago. Okay, so we're sort of always looking into the past. Okay, and the present, there's really no such thing as a global present. You know, everything is relative. We have our own local present where we can have strong consistency, but we can't do that across the network, etc. Each service have their own present. You know. Which might take some time to get over. You know, so microservices is really we're really diving into this sort of non-determinism of distributed systems, you know. And it's really a world where all bets are off. You know, messages can get lost, they get reordered, they get garbled, and you know, failure detection. If you're actually, if you I mean, to know if someone that the one that you're communicating with is actually down, or if it's just, you know, out for lunch, you know, doing GC or something like that, it's nothing but a guessing game. Actually, it's actually quite hard. But the interesting thing is this non-deterministic world that gives us, you know, tools for resilience, tools for elasticity, tools for isolation, things that the monolith couldn't really give us, right? But we need tools to model this uncertainty. You know, the hard things is the space between the services. It's actually quite easy to create a microservice. There are even like scaffolding tools that just let you do that very easily. But you know, that's the easy part. The hard part is defining the right protocols for this space in between. That's where all the messiness is. And how do you do that? You need well-defined protocols, you know. And as Pat Tellen said, a system that cannot count on distributed transactions need to manage the uncertainty in the business logic. It's your job to manage this uncertainty, unless you have, you know, the rare ability to use transactions, which is very rare, I think, if you want availability and scalability. So the question is, how can we do that? I also think that events can lead to greater certainty. I don't know if you know the work of Mark Burgess. That's he's a professor at Oslo University. He has been writing a lot of interesting articles and books around autonomy, you know, and how events and moving away from obligations or command and control can actually help us help us sort of end up with systems that are with really inherently autonomous components. And he said that an autonomous component can only promise its own behavior, you know. And why is that? Yes, because autonomy makes information local. You know, you can only sort of, since you can only promise your own behavior, you're only responsible for your own local state. And this is one of the reasons why I think these events and this inversion of control can really help us towards greater certainty and greater stability. Okay. And I think that, you know, events can really help us this view of events can really help us to craft these sort of autonomous islands of determinism and strong consistency. You know, islands that float around in this sort of wild ocean of non-determinism, sort of safe boxes where you can bring sort of sanity back, and we can actually reason about, you know, stable values and stable state. And the question, though, is, I mean, how do you sort of make all these islands work together? Yeah, one sort of mental model or mental framework that I learned from Pat Tell, and it was from one of his papers, is that he talks about first defining our inside data. You know, that's our current present. That's sort of what I talked about. You know, the box of sort of deterministic state, where we can assure strong consistency. That's our local state, okay? Then outside data, that he calls the blast from the past. That's our events arriving into our services, okay? That's facts. Between services, he almost like poetically called that hope for the future. That's the commands. That sort of asks you do between services. Ask someone to do something. Okay. Hopefully he will do it. Hopefully this command will eventually reach the sort of intended destination. Okay. But it's also important to understand that sort of a system of microservices is really nothing but sort of a never-ending stream towards convergence. We try to get there, you know, but since events and information has latency, we're always trying to catch up, and we will never ever really get there. We're always running behind full convergence. Because there really is no such thing as a single globally consistent now. Okay. So how can we sort of take these events then and sort of let them be the foundation for persistence? I said earlier that I think CRUD actually can work as at least a first step towards an event-driven architecture, and work well with the event streams. And the way we've seen many customers do this is by having if you have sort of two different services, Service A and Service B, and each one of them is using CRUD, storing state into the database. So Service A storing it in table A, for example, and Service B is storing it in table B. Okay, and then each one of these have an event stream. Now, if Service A then, in an atomic way, stores its records in table A, but at the same time, creates an event out of this change and pushes it to the event stream in an atomic operation. That's important. And Service B does the same. Okay, then we can have a Service C that subscribes on these two event streams, changes from Service A and changes from Service B. And it can then perform a join between table A and table B. Fully safe, in a safe context, without any transactions really across the network here. And then serve this join table to the outside world, to user. So this is a way of using events and the event stream to sort of get over this problem of that you can't have transactions, XA transactions, distributed transactions, but you still, are able to do joins when you have to. The important thing is that this really needs to be read-only, I believe, simply because you have eventual consistency going on here. Okay. But this can be a first step towards this pattern CQRS, if you heard about it. This is sort of the first stepping stone towards that architecture. But I think we can do better. And the fundamental problem with CRUD in the first place is that it's update in place. Jim Gray once said that update in place strikes system designers as the cardinal sin. It violates traditional accounting practices that's been observed for hundreds of years. I think yet again we need to relearn from the real world. How does the real world actually deal with this? What is actually fundamental accounting principles? With double bookkeeping and these things. I mean, we never use destructive updates, deleting all records when we do traditional bookkeeping. Why are we keep doing that when with our SQL databases, right? Why are we throwing away data constantly whenever new data arrives? There used to be a reason why we did that, or why we are doing that. Disk space used to be very expensive. So it was a good reason, but today the disk is really incredibly cheap. There's really no reason to throw away the previous data whenever new data arrives. There's no reason for this destructive update. And Pat Tellen, said that in one of his great papers that the truth is the log. Really, all these SQL databases they do event logging, really transaction logging under the hood. They only expose destructive updates and tables using CRUD to us as users. Okay, the question is why work with the subset of the real thing when we can work with the real thing directly? Just use the log. Okay, but to do that, we really need to apply the basic principles of bookkeeping, where we sort of use event logging, where we essentially store each event, each change of state in order as it arrives, without deleting the previous version. In a sort of append-only fashion, just like transactions in a ledger, one by one by one by one. And if we do that, then it can really be the bedrock for a lot of things, for things like consistency, availability, scalability, traceability, etc. And a great pattern for us to achieve that is event sourcing. How many people have heard about event sourcing in the past? Quite a lot of people, actually. I'm sorry. This is no news for you then. But it can really be sort of this cure for this cardinal sin of destructive updates, and can really be an excellent tool in achieving a scalable and a resilient architecture for microservices, I believe. And event sourcing really works the way that you log each sort of state changing event in the transaction log, essentially. To back up the aggregates. This means that you can have strong consistency within each aggregate based on this event log. While between aggregates, you have eventual consistency, since others can sort of subscribe to that log that you update atomically, but others can subscribe to that in an eventual consistent fashion. Okay, and the way it works is that. Let's first go through the happy path. Let's say you have some sort of user sending in a command to this event source service. It's up on its mailbox, and the command causes some sort of state change. That state change creates an event, and we store that event in the event log, in order, in an append-only fashion. 1 event, 2 events, 3 events, 4 events, etc. And this event log is what we do, what we use as our mean to serve other services through our event bus, because this is sort of we have one single sort of source of truth here, and that's our event log, which also others can subscribe to. If you remember earlier, it can be other services, other subsystems. You can shove things down into other databases and things like that. But one of the key aspects now then is what happens if this service fails. Okay. Well, in the sort of sad path here, we need to recover from failure. The first thing we do, of course, to sort of recreate our service, to respawn it. But the interesting thing, since every single state change that ever happened is stored in this event log, the only thing we need to do is just to replay the events and bring that component up to a healthy state. So it's really, really easy to recover from failure. And as I said before, other replicas can subscribe to this event. So there might not even be any latency. This can be an ongoing operation happening constantly, even though there's no failure. So as soon as there is a failure, you have hot replicas already up to speed that your load balancer can just point over to. And the really interesting thing is, and then as soon as that's done, you can start serving commands again like nothing has happened. The interesting thing is that you have one single sort of truth with all history that's ever happened in your system. Okay, in one place. And it allows for this, what Martin Fowler calls memory image. You can Google that, and he wrote up a post about that. That's essentially a fancy name for durable in-memory state. Your state is in memory, in your components, but it's still backed by a durable event log. So it's extremely fast to use. It's just in memory. Okay? But it probably more importantly avoids this infamous object relational mismatch that you have to map your object state or your functional state or whatever you kind of paradigm you use down to relational state representation. All this madness that we do, with Hibernate, JPA, and all that's just gone. You don't need to do that anymore. Okay, and also, as I said before, it's worth repeating, is that others can just subscribe to this event log as they wish. 0, 200, 1,000, for all kinds of purposes. And you have also bulletproof audit logging. It's right there in everything that's ever happened in the system is right there. You can sort of have an offline copy for debuggability that listens in. That's in a full safe environment. You can slow down the system and replay the event log slowly to see what happened in the production system when something went wrong, for example. Opens up a lot of possibilities. So, but sort of what about the event log and queries? That's a really bad match. It's hard to query the event log. And that's a fact, you know. This is one of the real strengths of SQL databases. So how to solve that? Yeah, here that's where CQRS come into play. It can sort of help us bring queries back into this model. You know, it's really CQRS means command query responsibility segregation. It's really about separating our write model, which now is storing events, from our read model, where I do my queries. To have two different separate models. And why is that? Yeah, because the read and the write model have very different characteristics. You know, first, I mean, it's really hard to query one and the other, and not the other. But they also have very different sort of consistency, scalability, and availability guarantees. And you know, in a read mostly system, for example, you know, you might want to scale up, you know, the read side, while the write side can be quite scaled down, and vice versa, right? So having them decoupled means that you have more knobs to turn for scalability and availability as well. So the way it works is that we have our user here again. He pushes in a command into our service that now serving our write model, pushing down into the event log. We know this already. Here we push our events, you know, through our event stream. But the interesting thing here is that we can have, you know, a second sort of view of the service subscribed to these events, now being the read side view. And the interesting thing is there, we've already talked about that the optimal state to store things in event-driven system is through an event log, you know. But what is the optimal way to store queryable state? Probably, you know, in a regular SQL database or a graph database if it's sort of graph-oriented, or it might be, storing it down to Hadoop or something like that if you have more advanced needs for doing, you know, analytics and things like that. You know, you have all options now. You can actually have multiple read models. One might be SQL database, one might be, you know, Spark streaming or something like that. And then, you know, the user does his queries on the read side model, while all the commands are update state in the event log on the right side. So this separation gives us a lot of, definitely adds complexity, you know. But if you're going for microservices, then you sort of asked for it already. You know, this is just a way to try to actually get away with actually some sort of order and some sort of good standard patterns in order to actually navigate these hard challenges that we have in managing sort of consistency in a distributed system. But I'd say, I mean, one of the key aspects here is that you can't have the cake and eat it too. You know, you have to sacrifice something, and what you sacrifice here is that you most likely will have eventual consistency. I say most likely because your event log can actually be the same database. So there is actually a way. I've seen clients do that, storing the events straight down into the SQL database that they serve the read model from in an atomic fashion because they can update two tables, the read side and the write side at the same time. So there's actually a way to get away with this without sacrificing eventual consistency. But a lot of clients also like the flexibility of this and also serving multiple read models and things like that, and then it might be hard. Okay. Finally, I mean, events really gives us a really good way of managing time. And time is probably the hardest thing to manage well in a distributed system. Greg Young once again said that modeling events forces us to have a temporal focus on what's going on in the system. The time becomes a crucial factor in the system. You know, and event sourcing really gives us a really good tool to model time. Because, you know, our event here is our snapshot in time. No? That we can store historically, so we know exactly what happened at a specific time. If the event ID is our index, or sort of our time cursor that sort of flows, that you can jump in, you know, and read at any point, replay from any time, etc. And our event log here is our full history, everything that's ever happened. This means that our database is no longer just a database sort of a view of what's happening right now. It's actually a full database of the past, of everything that's ever happened, you know. And that's actually the path to our present. Because, you know, as we said, knowledge accrue. So the sum of all our past actually gives us what we have today, right? And also, you know, I've hinted at that, but this event sourcing also gives us tools for things like time travel. You know, it sounds fancy, you know, but in software, it's actually not that hard. It gives us, you know, tools for doing replaying the log for historic debugging, as I said, in a safe, you know, backup system for debuggability, replay the log for auditing, for traceability, replay the log on failure for replication and things like that. And we can even actually fork the past. Even though that sounds really funky, it can actually be very, very useful when you want to upgrade a system, upgrade versions and things like that. You might want to keep on running, you know, one sort of reality while, you know, forking off and running the new reality, and at a safe point turn off the old one, for example, right? And this is also very, very easy if you use event logging. So key takeaways here: events first design really helps us to reduce risk when modernizing applications. It really helps us to move faster towards a resilient and more scalable architecture. It puts us on the right path to design really autonomous services, which actually goes hand in hand with resilience and scalability, in my opinion. And helps us to balance certainty within the aggregate, within the service, with the uncertainty between, you know. And being okay with that, being okay with uncertainty where it has to be, you know, because we can still play safely within our little tiny boxes, so to speak. Event logging allows us to avoid CRUD, avoid this impedance mismatch, ORM, and take control of the system's history. Allows us to do things like time travel and also balance strong and eventual consistency, as I talked about, which also can be very, very tricky. But having the right patterns and practices in place makes it a lot easier. Okay, I believe, personally, I've seen, you know, this being quite hard and quite overwhelming. So you really need good tools to do this. And of course, I mean, I'm coming from the ACA camp. We have a lot of customers that have been very successful applying ACA to this problem. ACA actually has direct support for all of the things I just talked about here. So I won't go through all of this, but it's really good stuff. It's made for mortals, so it's actually not that hard to use. I mean, just check it out if you're interested. aka.io. There's a lot of documentation and stuff there. If you're interested in more of these things, I wrote a little mini book. It's about 50, 60 pages or so that goes a little bit more into detail of what I talked about and puts it a little bit more in context. It's freely available from this URL, bit.ly reactive-microservices, if you're interested in reading more. I'll be around for the rest of the conference, rest of the day. So don't hesitate to come up and challenge me on these things or ask questions or whatever. I'm really here to try to get you on the right path and make you successful. So thank you.